Chapter 10, Rolling, Torque, and Angular Momentum. It covers rolling, Newton's second law in angular form, conservation of angular momentum, precession of a gyroscope. You can find them in the timeline. Rolling. Rolling as a rotation and a translation combined. We look at this wheel. It's rolling on the ground. The contact point is P. In this case, rolling, there's no slide. Okay. So in this case, the velocity at this point is 0. After time, T, it goes to this point. Okay. And this is S. And we know if there's no sliding, this arc is equal to the S. And this S equal to r theta or theta r. And the velocity of this center of mass is ds dt. We do the ds dt, we find the velocity center of mass equal to d theta dt omega r. Rolling as a rotation and translation combined. This is a pure rotation around the center mass O, plus translation together with the center mass. Everything has the same velocity at the center mass. And these two put together, we get this one, this rolling. You see, these two velocity equal and opposite, you put together 0. This is 0, but this one is V. And those on the top both have the V, so get a 2V. So this is rolling as rotation and translation combined. The velocity of the P is 0 because no sliding, okay? And the velocity of center mass is omega r. The wheel moves smoothly, no sliding. Rolling as a pure rotation. We can look at the rolling in another angle. All the wheel rotate around this ancient axis, rotation axis at point P. Okay. It's a pure rotation with an angular speed omega about the axis, this one, okay, that always extends to point P. And turns out this angular speed omega is the same angular speed the writer observes it in pure rotation about an axis through its center mass. Let me prove it. Before we conclude, we see the kinetic energy of the rolling. Okay. It has pure rotation, so this is half IP omega prime squared. Okay, pure rotation. If it's a rotation plus translation, so that the energy is rotation energy and the translation energy. Okay. And we say this omega is equal to this omega prime. How do we do that? You see, V-com equal to R omega squared. So equal to R squared omega squared. We'll take the omega squared out. We're going to have I-com plus mr squared plus omega squared. What are this term? I-com plus mr squared. This is actually is IP, right? From the parallel axis, this is a inertia to the center mass, so the center mass, parallel to the axis. This is everything's concentrated on the center mass, the inertia of center mass to that axis. Okay, so we got I-com plus mr equal to IP. Then we put them to C. These are different presentation. They should be the same. So pure rotation half P omega prime equal to this one, equal to rotation and translation. And this is the IP. So we compare these two, half IP omega prime squared, half IP omega squared, they're equal. So that means omega prime and omega are the same. A rolling object has two types of kinetic energy. A rotational kinetic energy have icon omega squared due to its rotation about its center of mass. And a translational kinetic energy have mv com squared due to translation of its center of mass. Example: a uniform solid cylinder disk is a disk of mass m 1.4 kilogram and radius r 8.5 centimeter rolls smoothly across a horizontal table at the speed 15 centimeters per second. What is its kinetic energy K? That's very simple. As rolling, you have a two part. Okay, the omega, the angular velocity speed, equal to v com over r. Now, this is my purpose. I will do this one. V com is 15 centimeter. We have it writing standard form. Length as unit meter. So 15 centimeter is 0.15 meter per second. This is the key point in this question. Okay. Yeah. So K equal to two parts, rotation part and translation part. We put everything in, you get the answer. The purpose I take this sample is this one. We have to use the standard unit. The force of rolling, friction and rolling. Rolling, you must have a friction. Okay? If the wheel rolls at constant speed and it has no tendency to slide at the point of contact P, and thus there's no frictional force acting on the wheel there. However, if a force acting on the wheel changing the speed v com of the center of the wheel or the angular speed omega above the center, then there's a tendency for the wheel to slide at P, and a frictional force acts on the wheel at P to oppose that tendency. Until the wheel actually begins to slide, the frictional force is a static friction force, Fs. If the wheel begins to slide, then the force is a kinetic friction force, Fk. Now, if some reason the wheel accelerates, it's rolling fast, then a point P on the wheel, it has tendencies to go up. So in this case, the friction opposite direct tendency goes forward. Okay, and the A com is equal to acceleration, angular acceleration, alpha r. Rolling down a ramps of ball. This is a ball. Okay. Now we set the reference. Let's set the x downward and the orange at point P. We see how describe its motion. We use Newton's second law. How many forces acting on this ball? You see the gravitational force, mg. Normal force, we don't know. And the friction force goes this way. Okay? Assume it goes this way. You can assume it goes down. Whatever you like. If you do it right, you get the same physical answer. Now let's write that formula. Along x direction, I have this force, mg sine theta minus f equal to ma com. About rotation, here this rotation, you see fr equal to I alpha. Okay. Now we have 1, 2, 3 unknown, only 2 equations. That's not enough. So we need one more thing, is to find the relationship. And from this rolling, we will find out the A com equal to R alpha. Right. With these 3 equations, 3 unknown, it's very easy to solve the answer. Okay. Now I just give the answer. From this one, could alpha can, in terms of A, and you get an F, put as F, we get an A. Okay? That's very simple one. Okay, that's simple one. Now, I want to discuss the answer. The answer is A acceleration is G sine theta over 1 plus I com over mr squared. I com is this one, the inertia of the center of mass. Previous we learned the sliding. Okay, we see A equal to G sine theta. Whatever mass is, it always have the same acceleration along inclined surface. But with the ruling, it's different. It has a one x term. So the A is smaller than the sliding. Okay, it's sliding. And the A depends on the icon. A different shaped stuff, and they have different icon. A.
It rolls down a slope. Here are two disks of different radius and mass.
They are the same shape. Icon is the same, so they have the same acceleration.
If we roll them down this incline, they reach bottom at about the same time. Here are a disk.
This time they're different shape,
mass.
different icon,
If we roll
so they
them
have different
down the
acceleration.
incline, one will roll faster than the other. Which one will reach the bottom first? The disk rolls faster than the hoop. Here are two wooden disks of equal
They are
mass.
different shape,
One has a heavy brass
different
center,
icon,
and the other
so they
a
have
heavy
different
brass rim.
velocity.
Which of these will win the race to the bottom? The disk with the heavy center wins.
This spool on an incline will be used to show what happens to a rolling body when the radius on which it is rolling is changed. When the spool is placed at the top of the incline, only the center hub is in contact with the incline. As the spool rolls down the incline, it acquires both translational and rotational velocity. What will happen to these two velocities when the spool begins to roll on the outer disks? The spool moves faster, but spins slower. Here's the action again.
This bicycle wheel has a weighted rim and an axle that can either rotate freely or can be locked to the wheel. If we put the wheel on this inclined track with the axle free to rotate, the wheel moves down with only the axle turning. If we lock the axle to the wheel so that they must turn together, how will the motion of the wheel change? The wheel now moves down the track much more slowly, but has a much larger amount of rotational energy when it reaches the bottom of the track.
This loop-the-loop track can be used to explore the relationships between energy, velocity, and centripetal force. If a ball is rolled down the track starting from just above the top of the loop, will it go around the loop? The ball falls off before reaching the top. We'll now release the ball from increasing heights.
Example. A uniform ball of mass m 6.00 kilogram and radius r rolls smoothly from rest down a ramp at an angle theta equal 30.0 degree. Question A. The ball descends a vertical height h 1.20 meter to reach the bottom of the ramp. What is its speed at the bottom? In this case, the friction does not do any work because the point P does not move at all. Okay, so we have mechanical energy conserved. Okay, this is the final kinetic energy, final potential energy, initial kinetic energy, initial potential energy. Here, potential is the gravitational potential energy. Now we write it down. At the bottom, it has two terms. One is the rotation term, and one is the translation term. Final, we set this level UF equal to 0. And in this one, so initial potential mgh, and initial kinetic energy 0. So that's it. And then we have a relationship, which is Vcom equal to omega r, okay, omega r. And Icom, this is the ball. We check the table, is equal to 2mr squared over 5. We put this one inside, we get the answer. I'm not going to do it, okay? This is a 4.1 meter per second. Now, the important thing is this one. If you know the physics, it's a very easy one. Question B. What are the magnitude and the direction of the friction force on the ball as it rolls down the ramp? Before, we assume the direction is going up, okay? And we have this location, RF equal to Icom alpha com. And alpha com equal to acceleration center of mass over R. What is the A? We also calculate this one. This A is special, equal to G sine theta 1 plus Icom over mr squared. In this case, it's a ball, so the Icom equal to 2mr squared over 5. And theta, we put everything in. Okay? Okay, let me see. This is theta is 30 degrees. That's it. Okay. Once we have A, we can find F. F equal to Icom A equals C over R squared. Okay, and Icom equal to 2mr squared over 5. We put in R squared, cancel out. We get this one is positive. What this mean? This mean is the direction is upward, as we assume. The yo-yo is a tool when we were kids, we play, give us so much fun. Okay, let's look at the free body diagram. The rams wrapped at the axis, small axis, are 0, very tight. And outside we have two big discs on two ends to increase the initial. And look at this free diagram. Fmg minus t equal to ma. And rotation T R0 equal to I alpha. And alpha A has a relationship Acom equal to R0 alpha. This is R0. Okay? And these three, it's very easy. We get A. Now, this A is similar to the A we rolling down the road, the incline. You look at this one. When Icom is very large, and this is large, the Acom is smaller. When R0 is very small, this turn is large, the A is small. This is what we want, okay? We want it is a very large Icom, very large, the disc on both sides, and very small radius R0.
This device works like a yo-yo turned inside out. When we wind it up along the string, we store gravitational potential energy. After it is released, that energy is gradually transformed into rotational energy of the disk. When the disk reaches the bottom of the string, it begins to roll back up. The rotational energy is gradually transformed back into gravitational potential energy. When the
Newton's second law in angular form. Torque revision. We talk about the torque, a force F, okay, relative to a point O, because the torque is R cross F, okay. This is the acting point, this is R, okay. R cross F means this torque is perpendicular to R. A torque is perpendicular to F. So in this case, when you use the right-hand rule, we go to R cross F. So the torque is along the positive direction. Okay. This is definition. And we rewrite it, and the cross product of the two vectors equal to RF sine phi, and the direction torque is V. And we combine F and sine phi, we get, because we call it RF perpendicular torque. What is it? Let's see, that's what. This is a phi, angle between F and R. This is a phi. F sine phi is this one. This one is the F's component perpendicular to R, okay? Also, we can combine R sine phi, because F R sine phi. What is R sine phi? R sine phi, we call it R perpendicular. What is this? You look at this one. This is F, this is R, this is phi. R sine phi is this one. This one is the component of R perpendicular to F. So finally, torque equal to RF perpendicular or FR perpendicular. Torque has a meaning only with respect to a specified origin. Here is the O. If F parallel to R, then phi is 0. Sine 0 is 0. That means torque is 0. Okay. The torque tends to rotate the body. Sample. In figure A, forces each of magnitude 2.0 Newton act on a particle. This is a particle. You have a three force, F1, F2, F3. Okay. The particle is in the XZ plane at point A, given by position R, this is R, okay, where R is 3.0 meter and theta is 30 degrees. Force F1 is parallel to the x-axis. Force F2 is parallel to the z-axis. And force F3 is parallel to the y-axis, or towards the negative direction. What is the torque about the orange O due to each forces? We look at this one. We find the torque 1. By definition, torque 1 is R cross F1. We look at this one. This is F1 along X minus C. So we look at XOZ. We move the R up. So this is R, this is F. So we use the right-hand formula. We roll this one. We find the torque one is inward the space, this place. So it's XZ is minus Y direction. Okay, and the magnitude is FR F1 sine phi. The angle you look at is 150. The direction is inward. This one is minus Z, minus Y direction. So this is X, Y, Z. The tall one is minus Y direction. Let's look at tall 2. F2 is here. So they are in XOZ surface. We moved R out. You see this angle, this is 30. So this is 90, so 120. Okay. And you use the right hand rule, you move this one here, you find the direction is outward the surface. Okay? That one is the positive y direction, x, y, z. Okay? The number is r f2 sine phi. That's phi 120. Okay? And the last one is f3, this one. So talk this r. We move this one. We find this f3. We look from x o z direction is inward. Okay, this r. So use the right hand rule. R cross f is this one. It is also in the x o z plane. Okay, and this is perpendicular to r. So this is this one. R3. The angle is 90 degrees. Okay. This is 3. Okay. And in mathematics, the cross product of two vectors can be expressed in matrix. IJK. This is XYZ. This is FX, XY, FZ. For example, in this case, okay, Rx is R cosine theta. Ry is 0. Iz is I sine theta. Look at F. F1 is minus F. F1 is Y0, F1 0. So this one, if you extend this matrix, you get a minus Fij is equal to minus 3.0 Newton J. Exactly this equal to this one. Okay? Angular momentum. We define for a single angular momentum particle is equal to r cross p, where r is its location, okay, the position, acting point r. The p is linear momentum mv, okay, and the m can take out m at the side. This is the definition. Okay, now let's look at this angular momentum carefully. Okay, we know this is always right hand rule. We extend our right hand along the four fingers along the y, and we rotate towards the p. That your extended thumb is the direction of air. Okay. Now we look at this one. We look at this one. The air perpendicular to r, perpendicular to v. So the air must be this one. Okay. The angular momentum in this case, because r cross p, so it's up. It's this right direction. Okay. We write this one. This is a unit angular momentum along the z direction in our case. Okay. The magnitude is mv r sine phi. The phi is the angle between the velocity p, angular momentum equal to r cross p. This is r, this is a p, okay? This is angle phi between them. We can combine this sine phi with different things, okay? They all have r, so we have to specify what kind of orange it is. Okay. Then we rewrite the magnitude, no direction. It's mrv sine phi. We can combine mv with sine phi. You can see mv sine phi is this one, p perpendicular. Perpendicular to what? Perpendicular to r. Okay. Also, we can write this one. Okay. We combine r sine phi. Okay. What is r sine phi? Look, this one. This is r. This is the phi. I sine phi. This one. We call it r perpendicular. Perpendicular to what? To p. Okay. So we call it the p r perpendicular. If v parallel to r, then the angular momentum is 0. Example. Figure shows an overhead view of two particles moving at constant momentum along the horizontal path. Particle 1 with momentum magnitude P1, 5.0 kilogram meter per second, has position R1 and will pass 2.0 meter from point O. This is the distance. Particle 2 with momentum magnitude P2 2.0 kilogram meter per second has a position R2 and will pass 4.0 from point O. What is the net angular momentum? L about point O of the two particle system. It's very simple. Just put in the formula. L1 equal to perpendicular RP1. Okay. Everything given. This is 2.0. This is 5.0. L2 equal to R perpendicular 2 plus P2. Okay. The only thing we have to notice is the direction. You see, RP, this is outward direction. RP, this is inward direction. So they are in opposite direction. So assume outward is positive, then this is negative. So when put them together, one is positive, one is negative. Newton's second law in angular form. We know Newton's second law in transform form. Sigma F equal to dP dt. P is the linear momentum. And when we do the angular relatively, then is sigma tau equal to dL dt for a single particle. Now let's prove it. Okay. What does this mean? This means the vector sum of all torque acting on a particle is equal to the time rate of change of the angular momentum of that particle. Of course, to the same orange. Let me prove it. You see, by definition, the angular momentum L equal to R cross mv. We do the derivative with respect to time t on both sides. This is two term. So what we do is we derivative the first term multiplied by 2. And when we derivative the second one multiplied by 1. And dr dt is v. So the v into c. And m is constant, take out. dv dt is 8. So this is m8. Okay? And we know v cross v is 0 because the angle is 0, sine 0 is 0. And this is a sigma f. Since r is one thing, it's only that one number. So we can put inside, you get a sigma r f. That is sigma tau. That we prove this one. dl dt equal to sigma tau. The sum of all torques acting on a particle is equal to the time rate of change of the angular momentum of that particle. Example. In a figure, a penguin of mass m falls from rest at point A down. Okay. This A is horizontally distance d from the orange O. And an XYZ coordinate system. This is X, this is Y. Z is outwards. X, Y, Z is outward. Okay. The positive direction of Z is directly outwards from the plane of the figure. Question A. What is the angular momentum L of the falling penguin about O? Now, by definition, it's very simple. R cross P. This is R at any time. P is going down, this one. R cross P by right-hand row is towards inside. It is a negative direction of Z, okay? Okay. So we put this, it should be R perpendicular P. R perpendicular what? R perpendicular to P. So this is one, this is a D. MV, V, because it's falling at rest, so V equal to GT. Okay, that's the momentum L. Question B. About the orange O, what is the torque on the pigeon due to the gravitational force Fg? The torque Fg around this one, by definition, is R cross P. R perpendicular F. R perpendicular is D. F is mg. Okay. From these two, we found dl dt is dmg. Right? The dmg is just equal to torque. This is the second law of Newton's second law in angular form. Conservation of angular momentum. The total angular momentum L of a system of particles is the vector sum of the angular momentum L of the particles. So the total angular momentum of the system equal to L1, L2, L3 plus NL equal to sigma I, Li from 1 to n. Now, let's do the derivative with respect to time t on both sides. This is the derivative of angular momentum. We look just when we put the derivative inside, we get sigma d dt Li. And the d Li dt equal to sigma tau I. And this is the total torque, sum of the total torque. And the torque can include two parts. One is external force torque, one is internal force torque. Okay. And we find out the sigma tau internal torque equal to 0. Why? Because the force always appears in pairs. Okay, and their torque we put together is 0. So combine these two, we get sigma external torque equal to dl dt. This formula is the angular momentum of a system particle. It's similar to sigma f internal equal to dp dt, the system linear momentum derivative equal to the sigma net force. Okay. This is the Newton's second law for rotation in angular form. The net external torque, acting on a system of particles, is equal to the time rate of change of the system total angular momentum L. This equation, of course, have to refer to the same orange. Okay. In an inertial reference frame, it can be applied with respect to any point, this point, the reference point. In an accelerating frame, such as wheel rolling down a ramp, it can be applied only with respect to the center of mass of the system. Before we go on, we have some review. We see a position R equal to xi plus yj with a zk. If we dot R with I, and we find I dot I equal to 1, I dot j equal to 0, I dot k equal to 0, so R dot I equal to x. Same reason, y equals R dot j, z equal to R dot k. Now, following, if we have air I, we want to find the z component, we just dot k. Okay. Another formula is a cross b dot c. You can rotate, put a motor down with b cross c dot a, and then b turn back, c cross dot a. Okay, actually this is a matrix like ax ay az, bx by bz, cx. They can rotate. They get the same value. Now let's go on. The angular momentum of a rigid body rotating about a fixed axis. We look this is a rigid body. This is a fixed axis C. Okay, this is x, y. Oh, let's look at one point, delta mi, this point, its location is Ri from O. And its angular momentum around this O is Ri cross Pi. This is Ri. Velocity is Pi. This should be perpendicular to the z-axis, perpendicular to its radius, right? The velocity. Okay. Now, Pi equal to delta mi vi. Okay. I want to find the z component of this vector, Lik. As we studied before, we just use this one dot k. And Li is Ri cross delta mi vi dot k. This is A cross B dot k. It can be rewrite at B cross C dot A. Okay? Now, that looks like this one. Suppose this is called a unit vector R perpendicular to the P. This is a radius, okay? This is units. Now look this one, okay? This is equal to Vi cross K. The magnitude is delta mvi. This cross K, okay, equal to this cross K equal to this direction. Clear? Now, Vi, this one. Z, this one. You use the right hand curve, you get this red one, what called R perpendicular. What is R perpendicular? Is a unit vector. It's a unit vector, okay? It's both, okay? In direction of the radius of the circular path of the nth mass element. This is R. This is unit vector, okay? And then this is a dot. So we take this out and we find that R perpendicular dot I. We just learn this is a unit vector, this is Ri, this is equivalent to the component along Z R perpendicular the Ri. Actually, this is a number because we'll call it R perpendicular I. This is a radius of this particle, okay? Radius, okay? So Ri is a number, is a perpendicular distance between the ith element and xz axis, okay? Now, since Vi equal to omega Rii, this is Vi rotate equal to omega V Ria. So we put this inside, we get this one equal to delta M R perpendicular I squared omega. Now, this one is the I's. How about the total? Number total Z is sigma Liz is sigma this one. And this omega is a constant. It's true for everybody. You take it out of the sigma. And what is this? Sigma mr squared. So this is the initial, angular initial around this axis Z. So we have Lz equal to Iz omega. Then we get L equal to I omega. This is the vector equation, okay? It has three components, okay? Conservation of angular momentum, okay? So far, we have discussed two powerful conservation laws: the conservation of energy, the conservation of linear momentum. Now, we met a third law of this type, the conservation of angular momentum. dl dt equals sigma tau external, okay? If no net external torque acting on the system, this equation becomes dl dt equal to 0 or L is constant. This is an isolated system, no contact with outside, okay, because this is 0. This result, called the law of conservation of angular momentum, can also be written as air initial equal to air final. Okay. If the net external torque acting on the system is zero, the angular momentum air of the system remains constant, no matter what changes take place within the system. Air equal constant, this is a equation, vector equation. So it will have three component equation. They are independent with each other. If the component of the net external torque on the system along a certain axis is zero, then that component of the angular momentum of the system along that axis cannot change, no matter what changes take place within the system. This is a three independent component. Like the other two conservation laws that we have discussed, the conservation of angular momentum holds beyond the limitations of Newtonian mechanics. They hold for particles whose speed approach that of light, where the theory of relative reigns, and they remain true in the world of subatomic particles, where quantum mechanics rules. No exceptions to the law of conservation of angular momentum have been found. When r smaller, inertia smaller, so the angular velocity should be larger. And also the gravitational potential transfer the kinetic energy. So that's why it's wrong.
As the marbles
The omega
approach the
gets
bottom
bigger
of
and
the funnel,
bigger.
their radius of rotation decreases. As the radius decreases, the rotational velocity increases, conserving angular momentum.
This circular train track rotates freely on a bicycle wheel bearing. After this wind-up train is released from rest, the train moves clockwise while the track moves counterclockwise. The angular momentum of the system, which was initially zero, is still zero. When the train runs down, both train and track slow down and stop. This bicycle wheel rotates freely on a bearing support. An outer metal frame also rotates freely on a separate bearing. A spring-loaded brake attached to the outer frame connects the two so that they rotate together. We'll tie the brake back with a string so that we can spin the inner wheel. Then we'll burn the string. When the burning string snaps, the brake clamps the frame to the wheel, and they spin with a rotational speed that is less than that of the wheel alone. If we increase the mass of the outer frame and repeat the demonstration, the final speed is even smaller than before.
We now discuss 4 examples involving this law. The spinning volunteers. You see this guy sit in the chair with 2 dumbbells. Is there the force? Yes, gravitational force, and the chair, normal force. But these 2 forces, without any torque around this axis, because they parallel, okay? At the beginning, we rotate it. Okay, it has an angular frequency. If he moved his hand in this way, the inertia gets smaller. So by the conservation of angular momentum, the final velocity, angular velocity, should increase. In this sigma tau, external equal to 0. So I IIFI equal to IFFI. Okay, if the I decrease, the frequency must increase. Okay, okay, we see this one.
You've probably seen an ice skater perform a spin. We'll use this rotating stool and a pair of handheld weights to demonstrate the same effect. After a person holding the weights out at arm's length is spun, she rotates at a constant angular speed. When she pulls the weights closer in, her angular speed increases. Moving the weights back out slows her down. This animation shows the action from above.
To the spinning board diver, you see the Olympic race. You look at this point, center mass is parabolic, okay, like a single particle. And you want to do some action, you have to tuck your body. So why? Because in this case, the inertia is smaller, then omega can be larger. When you go diving in the water, you need to stable, so you have to open layoff position. Okay, the center of mass follows a parabolic path. Okay, referring to the center mass, because all the torque equal to zero, you have a gravitation force, but towards the center of mass, the torque is zero, so it's air angular momentum constant. 3. Spacecraft orientation. In spacecraft, we have a flywheel. Okay, when you want to adjust the location of the spacecraft, we rotate the flywheel. Why? Because this is an isolated system. The total sigma external torque is zero, so its angular momentum conserved, which is equal to I spacecraft, omega spacecraft plus I flywheel and angular velocity flywheel. Okay, we cannot, because originally the angular momentum is zero, and it conserved, so this one equal to zero, and then we get the omega spacecraft equal to minus the ratio. This is given, this is given, this we can control. In this way, if we do the integration with time, we get the delta theta spacecraft equal to minus this kind of the flywheel's angle. We can adjust the delta theta flywheel to control the spacecraft's rolling.
This man is sitting on a stool which is free to rotate. We'll give him a long bar with heavy weights on it. When the bar is rotating in one direction, he rotates in the opposite direction. If we move the weights further out on the bar and repeat the demonstration, will he now rotate more, less, or the same amount as before? He rotates more than before. This animation shows the motion from above.
This large metal disc is free to rotate on a bearing. A pair of smaller discs is attached to the outer edge. They can be released from the larger disc by pulling a trigger in the back. The large disc is spun by pulling on a cord wrapped around the axle. When the small discs are released, they will fly out on cables attached to a separate bearing. Here's what happens when they are released. The large disc stops, and the small discs revolve at high speed. Let's watch that in slow motion. What will happen if we add extra mass to the smaller discs and repeat the demonstration? large disk spins backwards.
Four, the incredible springing star. When the nuclear fire in the core of a star burns low, the star may eventually begin to collapse, building up pressure in its interior. This collapse may go so far as to reduce the radius of the star from something like that of the Sun to the incredibly small value of a few kilometers. The star then becomes a neutron star. Its material has been compressed to an incredibly dense gas of neutron. During this shrinking process, the star is an isolated system, and its angular momentum L cannot change. Because its rotational inertia is greatly reduced, its angular speed is correspondingly greatly increased to as much as 600 to 800 revolutions per second. For comparison, the Sun, a typical star, rotates at about 1 revolution per month. Sample. Figure A shows a student, again, sitting on a stool that can rotate freely about the vertical axis. Okay. The student initially addressed is holding a bicycle wheel whose rim is loaded with lead and whose rotation inertia I wheel about its center axis is 1.2 kilogram-meter square. The wheel is rotating at an angular speed omega wheel 3.9 revolution per second. As seen from the overhead, we see from the top. The rotation is counterclockwise. What this means it's positive number. The axis of the wheel is vertical, and the angular momentum L width of the wheel points vertically upwards. See this one. The students turn inverse the wheel so that, as seen from the overhead, it is rotating clockwise. That means omega is negative number. Its angular momentum is then minus L wheel. The inversion results in the stool and the wheel center rotate together as a composite rigid body about the stool's rotation axis, with rotational inertia IB 6.8 kilogram-meter square. The fact that the wheel is also rotating about its center does not affect the mass distribution of its composite body. Thus, IB has the same value whether or not the wheel rotates. Now, we rotate this up. Now it's going down. Okay, it's going down. And then the student wrote with this system. With what angular speed omega b, and in what direction does the composite body rotate after the inversion of the wheel? Originally it's going up, now it's turned down, and then it started to rotate. I want to find the angular speed and the direction. We know that's one. In this case, you have a gravitational force, have a normal force from the stool, but all these force does not have torque around this axis because they are the same parallel. So in this case, the angular momentum is conserved, and that means L beach final plus wheel final equal to L beach initial plus wheel initial. Now we put this number inside. This is angular momentum conserved before, after. Okay. Now let's book this one inside. The final angular momentum of wheel is equal to minus initial wheel because you turn around. Okay, and this initial the slope is 0. Okay, and I want to find this one. It's very simple. So we put this one equals to 2 is y. That's very simple. Okay, and when you write it out, what it is IB omega b. This is a 2I wheel omega wheel. Okay. And we find the angular velocity omega b equal to 2I where. So when you put a number inside, we get a number 1.4 revolution per second. Sample. In the overhead view of the figure, 4 thin uniform thick, this is 1, 2, 3, 4, each of mass big M and length d 0.5 meter are rigidly connected to a vertical axis. This is the vertical axis, okay, to form a turnstile. The turnstile rotates clockwise, that's negative number, okay, about the axis, which is attached to a floor, with initial angular velocity omega I equal to minus 2.0 radians per second. A mud ball of mass m equal to m over 3, and initial speed 12 meters per second is thrown along the path, shoot, and stick to the end of the wood rod. What is the final angular velocity omega f of the ball turnstile system with ball stuck here? We look at this. This is sigma tau external equal to 0. Do you have a force? We check. When you hit this one, we do have a force. Okay, acting on this one, the gravitation force, whatever. Okay, and then towards this axis, these forces torque is 0. Okay, so the totally sigma external torque equals 0. Then the angular momentum of the system conserved. So then we write it detail. Initial, final. Okay. Final, we have 2. One is the turnstile, one is the ball. Initially, you have 2. One is the turnfly and the ball. And we write it down. Okay. Look at this one. The hit here. So this is the R, and its P is MV. Now we see, what is this? What is this? This is a R cross P. R cross P, which is outward from the surface. What is the angle? Now this is angle. RP, this is 60, this is 90. So this is 60 plus 90, 150. Okay, whatever. So D is R. P is MVI. Angle is 90 plus 60. So this is cosine 60. Okay. And we see this one. Final. This one, we can find it. This one we want to find. This ball, initial, this is very simple, is mr squared, md squared, right? Yeah. So let's see initially. Initially you have rotate m versus I. And this one you have a d PMV cosine 60. That's all. But this is each one you have a 4. Each one is md squared over 3. Okay. What is this? This is stuck here. So that's equal to md squared. And this one is 4 md squared over 3. This one we have calculated. Okay. This one is given. This one is fine. So finally, we find omega f equal to 0.80 revolution per second. This is a positive number. What this means? That means after the hit this one, the rotation turnaround is counterclockwise. Precession of a gyroscope. A simple gyroscope consists of a wheel fixed to a shaft and free to spin about the axis of the shaft. That's the one. Okay, you have a rotate and you can around this one, this shaft. Okay. If one end of the shaft of a non-spinning gyroscope is placed on a support as in the figure, this is the one. Okay, and the gyroscope is released. The gyroscope force by rotating downwards about the tips of the support. Now, let's see. Originally, it does not have any rotation, non-spin. And then you have a torque because the gravitational around this point is mgr. So when you fall, it fall down. It will rotate around y direction. Okay. It is governed by Newton's second law in the angular form. Okay. We will see that. Okay. Tau equal to mg this is 90 degree. It's around the y direction. Okay. Now, originally it does not move. Okay, not a spin. So L 0 time is 0. Okay. And then we will see that you have a tau, so dl is L final minus an initial is L, should be around the y direction. So it will fall down, rotate. If you have a spin, a rapidly spin gyroscope, it behaves differently because it has initial non-zero angular momentum due to the spin. This is so initially it is I omega, we see along the x direction I. Okay, and then we have a torque around the y. This is mgr. This is a torque. So what I see is the dl have to change. The dl should along the y direction. Okay, it must rotate about the vertical axis z. I call it xyz. Originally, you spin around x axis, and you have a torque around y axis, and it turned out you rotate around z axis. So you see this one is L, rotate. dl should along the y direction in our case, torque. And at this, you look at the circle, the dl is tangent to the circle, dl. Okay, dl. Then when see what it do, initially it is around the z-axis. So this is xyz. You have an original angular momentum along x direction, and you apply a torque around y direction, and it rotate along z direction. Precession rate omega can be calculated as following. By Newton's second law, dl equal to tau dt, and the tau in this case is mgr. It's along y direction, dt. The increasement angle d phi in this circle, this is angle d phi. This angle equal to the arc dl over L. So d phi equal to dl over L, and dl equal to mgr dt. And L is I omega. I is the rotational initial of this disk around x-axis, right? Omega is its angular velocity. So the precession rate omega equal to d phi dt over this one equal to mgr over I omega. When omega is increased, very large, this omega precession rate is very small, decreases. Okay. This result is valid under the assumption that spin rate omega is rapid, very large. Okay. Because I is a function of m. Mass cancel out from above equation. So the omega is independent of the mass. Above equation also applies if the shaft of the spinning gyroscope is at the angle to the horizontal. Next lecture, Chapter 11, Equilibrium and Elasticity. welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.